Hi class, welcome to another session on digital principles and system design. Today we are going to study gray to binary converter. Now, gray to binary converter, if you have a gray digit or a gray number and you want to convert it into binary, then how you do it is by taking the MSB or the most significant bit as such in the binary section and adding the currently calculated binary number to the next you know to the next of the gray number. Like if I'm starting from MSB, then if MSB is the eighth position bit, then fourth position bit would be the next number. So if you see, this diagonal addition like the picture is depicting. So this is how you'd convert a gray number to a binary number. Suppose I have 1101 as a gray code and I need to convert the binary. I need to find the equivalent binary. Then how I do that is I write 1101 as it is, and then the one from the most significant bit is taken as the first most significant bit of the binary number. Now this most significant bit is added to the next bit of the gray number, and then the sum, whatever the sum is, that is taken as the third bit of your binary number. Now again, if a carry is generated, then the carry is ignored. It's just a sum that is taken into consideration. Therefore, 1101, if that's the gray code, then the equivalent binary is 1001. Right? So this is the logic behind converting gray numbers to binary numbers, right? So if I have to do it through a circuit, right? So how am I going to do that? So for that, let us start with a case study where I need to design and implement a 4-bit gray to binary converter. Now, the input here is the 4-bit gray code and the output here is the 4-bit binary. So let me take G1, G2, G3 and G4 as the gray input, where G1 is the least significant bit and G4 is the most significant bit. And B1, B2, B3 and B4 are the corresponding binary bits. Again, B1 would be my least significant binary bit and B4 will be my most significant binary bit. So if I go to the truth table, the one in the light color is the binary number, is the gray number. The one in blue is the binary number, binary equivalent. So I've just written a truth table where I've written the gray numbers from 0 to 15, and then I've written the equivalent binary numbers for it. So if we observe, G4 is same as B4 because we are taking the most significant bit as the same, right? So that's why you don't have to, even if you draw the K map and simplify, you can still see that G4 and B4 are equal. Now if you see here, if I populate the output B3 is 1 when I have the following inputs: 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 1 and 1 0 1 0. So if I populate my K map here, then I see that row number 2 and row number 4 are ones. Again, please pay attention to how I have populated the K map. I've taken G4 and G3 as the rows and G2 and G1 as the columns. Now, like I've said before in K maps, it's not mandatory that you have to take G4, G3 and G2, G1. You can take it in any sequence that you like. However, when you're populating your K map, you have to be extra careful, because these are the inputs. This is G4 is the most significant bit and G1 is the least significant bit. So when you're populating the K map, make sure that you're populating it according to the proper inputs. That's what matters. Now, for my combination, I can see that row number 2 and row number 4 are ones, which is like very simple, very pleasing to eyes. It's very easy to simplify. And this K map simplifies to exclusive OR of G4 and G3. So therefore my B3 becomes G4 exclusive OR with G3. Now here for B2, the life is slightly complicated. because B2 is 1 when you have the following inputs: 0010, 0011, 0100, 0101, 1111, 1110, 1001, and 1000, right? So here you can see that I have, excuse me, pairs of twos, right? I mean, pair is always two, but still. So here you have group of two ones, but you can't group any four together. So it has a kind of checkerboard pattern, and I have to take. I mean, this is the best I can simplify this K map. So what I do is I write the simplified version of each individual ones, which ends up being G4 dash G3 dash G2 plus G4 dash G3 G2 dash plus G4 G3 G2 plus G4 G3 dash G2 dash. Now, if I take G4 dash common from the first two terms and G4 common from the second two terms, this equation finally simplifies to becoming G4 exclusive OR with G3 exclusive OR with G2. Now G4 and G3 are exclusive OR in order to get our B3. Therefore, B2 can be simplified as B3 exclusive OR with G2. Now the purpose we are doing this is because exclusive OR is a two input logic gate. You can't have three inputs for exclusive OR. Therefore, in order to simplify three inputs, you have to have two gates. Now the first two exclusive OR is already being done by another logic gate, so I'm just using that output. Now again P1. P1 is a beautiful checker box and the K-map, because P1 is 1 when you have the following inputs, that is 0001, 0010, 01111, 0101, 0100, 0101, 1101, 1110, 1011, and 1000, right? So generally this checker box simplifies to be exclusive OR. Now, since there are no pairs, this we have to write all the min terms for this particular K map, which is what I've done. And if you do the simplification, you will find that G4 exclusive OR with G3, exclusive OR with G2, which is exclusive OR with G1. This would be your simplified equation for this particular min-term expression or min-term Boolean expression. Now, we know that G4, G3 and G2, when they are exclusive OR together, we get B2. So I just exclusive OR B2 with G1 to get my B1. So if I want to realize this as a digital circuit, then I use three exclusive OR gates. Now my G4 is B4 is same as G4, so I don't need any logic gate there. G4 and G3, when they are exclusive OR, I get B3. Now, in order to get B2, I have to exclusive OR B3 with G2, which is what I've done here. And in order to get a B1, I have to exclusive OR B2 with G1, which is done in the third logic gate, or the third exclusive OR gate. So this is how you would realize a gray to binary converter. I hope you had a fruitful session learning with me, as I'll see you again with another video. Thank you.